Okay, you can entitle this Heat and Thermodynamics Part 2. And why don't you show all the kids who were in here for this one? Hey, by the way, did anyone sign anything that says you can't be on TV?
Sure.
You're pretending, huh? Okay, here we go.
Right.
Okay, ready? Why don't you sit so it doesn't wiggle too much? Okay, first of all, A goes to B. This would be an endothermic reaction. Heat is being absorbed. So it would be A plus energy goes to B. Okay? This line right here, potential energy of reactants. Right here, potential energy of products. Right here is delta H. That's the value that would go right here. It would be a positive number because B has more potential energy than A. This line right here would represent the activation energy of the forward. Right here is activation energy of the reverse. Right here is the potential energy of the activated complex. Now, the activation energy is the minimum energy needed to get a reaction going. The higher the activation energy, most likely the slower the reaction. So we can add something to a reaction to lower the activation energy, and that would be a catalyst. There's what a catalyst would do. Okay? Now, if we did the reverse reaction, that would be an exothermic reaction. That would be B goes to A plus energy is released. Delta H would be the same interval, but they would be opposite signs, right? If the forward is endo, the reverse is exo. If the forward has a positive delta H, the reverse has a negative delta H. Okay? So now, the next thing that we looked at was this, right here. Heat of reaction is defined as the heat of formation of products minus the heat of formation of reactants. And you can go to your reference tables and you can actually look up the heats of formation. The heats of formation are given in Table P. So why don't you guys take out your Table Ps right now. This tells you how much energy is gained or lost when 1 mole of a compound is formed from its free elements. The amount of energy gained or lost when 1 mole of a compound is found from its free elements. Table P. Now, aluminum oxide has a heat of formation of negative 1675.7 kilojoules per mole. That means when aluminum and oxygen combine to form 1 mole of aluminum oxide, 1675.7 kilojoules of heat are released. Ready? Here's the rule. The more negative the heat of formation, the more stable. The more negative the heat of formation, the more stable. The more positive the heat of formation, the more unstable. Okay? Now, the next thing we looked at after this was something called delta S and delta G. Delta S is change in entropy. Entropy, randomness, confusion, disorder, chaos. Then delta G is called Gibbs free energy, of formation. Now, delta G, if it is positive, means it's not spontaneous. If delta G is negative, the reaction is spontaneous. That's what the values of delta G tell you. If when you calculate delta G, which is the Gibbs free energy of formation of products minus the Gibbs free energy of formation of reactants, products minus reactants, if you do that and you get a negative number, that means this reaction will spontaneously occur. If it's positive, it won't occur. Now on this table, on table P, why don't you guys look on table P, this gives you the Gibbs free energy of formation of all of these compounds. So what does it mean? Aluminum oxide is negative 1576.4 kilojoules per mole. This is delta G. What does it mean? Because it's negative, aluminum oxide spontaneously forms from its free elements aluminum and oxygen. It just means it spontaneously forms. Now, delta S. We don't have a table of S values. So that means there's only one other way for you to calculate delta S. It could be products minus reactants, but you don't have the S values. So that's where you're going to use this formula right here. Delta G is equal to delta H minus temperature times delta S. So if you can find delta G, and you can find delta H, and you know the temperature, you can solve for delta S and plug it in. Now there are two tendencies in nature that you have to remember. Number one, most reactions proceed in an exothermic direction, so that products have lower energy. Most reactions proceed so that the products will have lower energy. The second tendency is that most reactions proceed so that entropy increases. It becomes more disorganized. So, most reactions proceed so that delta H is negative and delta S is positive. And look what happens. Delta G is equal to negative minus a positive. You're always going to get a negative number then. So that's going to make something spontaneous. Okay? So you always go to low energy and high entropy. Okay? The end.